I just realized I wasn't recording. So suppose we had H2O molecules moving at around 110 degrees Celsius at a speed of 200 meters per second. If we replace the H2O molecules with O2, but kept the temperature at 110 degrees Celsius, so the temperature doesn't change, how fast will the O2 molecules be moving at? So temperature is equal to average kinetic energy. The equation for kinetic energy is 1/2 times mass times velocity squared. Water has a molecular weight of about 18 grams per mole. Oxygen has about 32 grams per mole. Again, you need to actually calculate the precise value. One oxygen molecule is 15.9994, so two of them is roughly 32. I'm just approximating for just to do an example. So we can let the mass. So in order for us to do this, we know that if they're at the same temperature, they're going to have the same average kinetic energy. So I'm going to say that we replace 1 mole. It doesn't matter how many, but we just need the exact equivalent. So we replace 1 mole of H2O with 1 mole of O2, for example. That means that we have a mass of H2O would be equal to exactly 18 grams, and our mass of O2 will be exactly 32. Or I shouldn't say exactly, would be approximately, because I'm not using the exact values. Again, you would have to look up. It's really 18.0125 or 00125, something like that. So this symbol right here, these two tildes, mean approximately. So we have a mass. Let's calculate the average kinetic energy of all the water, molecules. So the average kinetic energy would be equal to 1/2 times the mass of the water molecule times the velocity of the water molecule squared. So 1/2 times 18 grams. We know from the problem that they are moving, each of them are moving at 200 meters per second squared. So we can plug in 200 meters per second. And then we square that. We can do the same for the O2 molecules. The kinetic energy over here would be equal to 1/2 times the mass of the O2 molecules times the velocity of the O2 molecules squared. So this would equal 1/2 times 32 grams times the velocity squared. And this is what we're solving for. The problem says, how fast are the O2 molecules moving at if they're at the same temperature? So these two must be equal because temperature is average kinetic energy. That means the kinetic energy of the H2O molecules has to equal the kinetic energy of the O2 molecules. So we can set these two things equal. So 1/2 is on both sides, so we can cross that out. I can divide by 32 on both sides. 32 grams cancel out on this side. The grams cancel out on this side. So 18 times 200 squared divided by 32 gives me 22,500 meters squared per second squared. So 22,500 meters squared per second squared. And that is equal to the velocity of the oxygen molecules squared. To get rid of the square root, we take the square root of both sides. This square cancels out with this. And so we get 150 meters per second is equal to the velocity of oxygen. So that means that if this room were replaced with O2 molecules and they were moving at 200 meters per second, and if we, at some temperature, I really shouldn't have specified 110 because this doesn't work out mathematically. 200 miles an hour isn't the speed of water molecules at 110 meters per second, but it doesn't really affect the problem. All this really states is that they're vibrating differently. But anyway, this is how you would solve it. The key insight is that you need to find the kinetic energy of one molecule, find the kinetic energy of the other. These two must be equal if they're at the same temperature. So any other problems you had difficulty on? So if there's no particular question, let's work out some examples. Let's see. Contains 2 liters of air. Its pressure is at 1 atmosphere. And the temperature is at 70 degrees Fahrenheit. If the cylinder were left outside and the volume of gas decreased to 1 liter, what is the temperature outside? So a closed cylinder contains 2 liters of air. Its pressure is at 1 atmosphere and the temperature is at 70 degrees Fahrenheit. If the cylinder were left outside and the volume of the gas decreased to 1 liter, what temperature is outside? What is the temperature? What is the temperature outside? Assume gas stays at 1 atmosphere. So pressure is constant. So this is a standard gas law problem. Initial pressure times initial volume over initial temperature has to equal to final pressure times final volume over final temperature. So pressure stays constant That means we can remove it from the equation. So basically, you had a 2-liter empty Coke bottle in your car. It was 70 degrees during the day whenever you sealed it. But you left it in overnight, and the volume, it shriveled up by half the volume. That's something typical. But let's say you wanted to, so you walk out in the morning and you see this bottle and it's about half the size. You want to figure out exactly what temperature it is outside. You can use the gas law to actually figure out the temperature without using a thermometer. If you knew that when you sealed it up, the car said it was 70 degrees, and if it's at half the volume, you can calculate what the temperature should be. So, our initial volume is 2 liters. Our initial temperature is 70 degrees Fahrenheit, but we need to convert that into Celsius, or to Kelvin. So to convert into Celsius, it would be we take its temperature, 70, degrees Fahrenheit, we minus 32 degrees Fahrenheit, and we multiply this by 5 nights, and that gives us 21.1111 degrees Celsius. Then we add 273.15, and that gives us 294.2611 Kelvin. So we use temperature in Kelvin. We know that the final volume was 1 liter, and we're solving for final temperature. So we're solving for T2. Bless you. So what's the first step in solving this algebraically? So I have V1 over T1 equal to V2 over T2. What's the first step to solve for T2 using algebra? Again, this class uses algebra, but this is not an algebra class, meaning that I don't teach algebra. You're expected to know it before you come in. So what's the first step? Nope. So if your x value you are solving for is on the denominator, first step, put it on numerator. You cannot solve for something that's on the denominator, so you have to flip it to numerator. To do it, we can multiply both sides by T2. T2 divided by T2 cancels out on the right side. And so we're left with T2 times V1 over T1 is equal to V2. Again, we're still solving for T2, so what do we do now? There's 2 ways you can look at how to solve this. So we have something multiplied by our variable. We can either divide both sides by that something. So if we have 1/2 times x is equal to y, or let me do this. We have 1/2 times y is equal to x. You can either divide both sides by a half and end up with y is equal to 1 over 1/2 times x. That's valid. 1 divided by a half. So 1 divided by 0.5. How many times is 0.5 going to 1? Twice. So that's equal to 2x. Or, you can, if you have 1/2 times y equal to x, you can multiply by the reciprocal. So this is being multiplied. So y is being multiplied by 1. So we divide by 1. Y is being divided by 2. So we multiply by 2. Or you can look at 1/2. The reciprocal of 1/2 is 2/1. So 1/2, reciprocal is 2/1. The 1's cancel out. The 2's cancel out. And we're left with y is equal to 2/1, or 2 times x. So you can either divide or multiply by the reciprocal. So T2 V1 over T1, we can multiply the left side by the reciprocal. So multiplying by the reciprocal, T1 and T1 cancel each other out. V1 and V1 cancel each other out. And so your final temperature is V2 times T1 over V1. So volume 2 was 1 liter. Temperature 1 was 294.2611 Kelvin. Divided by a volume 1, which is 2 liters. Liters cancel each other out, leaving us just with the temperature, Kelvin. So that's equal to 147.13055 Kelvin. And converting it back into Celsius, we would subtract 273.15. So negative 126.01945 degrees Celsius. And then to convert this into Fahrenheit, we take this number, we do 9/5 times negative 126.01945 degrees Celsius, and we add 32 degrees Fahrenheit. All right, you remove the Celsius. And you get a temperature of negative 194.83501 degrees Fahrenheit. So basically, you're looking at like a 2012, was it 2012? Or no, Tomorrow Never Comes? What's the name of that movie? The Day After Tomorrow was the name of that movie. The Day After Tomorrow, when they started having, like, the storm got over an area, the temperature went from, like, normal all the way down to, like, negative 200 degrees Fahrenheit, and it started freezing the fuel in the helicopter and it crashed. So, if you go out and you see a 2-liter cup bottle at 1 liter, that's probably the least of your concerns. Which one? Mm-mm. So if you're not good at algebra, you need to be practicing and trying to follow along. Yes, you could have plugged numbers in at the very beginning and it would have simplified it. Because this would have been 2 divided by 1, so you would have had or this would have been v1 over t1, so you would have had 2 divided by this, and you would have just moved it over and divided. I used pure algebra until the very last step. How many of y'all are planning on the college? So when you get to college, you'll stop seeing numbers. It'll be pure algebra. It'll be so the question would have been, what is the final temperature? This would have been your answer. Your final temperature is whatever your final volume was times your initial volume divided by your initial. It'd be final volume times the initial temperature over initial volume. For chemistry, because it's actually applied science, they would actually have you come in and probably for chemistry, you probably would plug in all these numbers. But in most science classes, and particularly all the math classes, they end up the only number you really see is 2, because there's a lot of halves and there's x squared and stuff like that. But in college, it's going to be mostly pure algebra a lot of the time. And they all teach similar to this, where they don't plug any numbers in. Actually, the professor would have been like, V1 over T1 is V2 over T2. Obviously, T2 that means that T2 is equal to V2 times T1 over V1. And then you plug in. I mean, if you can go from here to here by just looking at it, that's fine. This is how I do my algebra. How you do your algebra could be different. Again, this is not algebra class. I expect you to be able to do algebra on your own, however you were taught. It's 31.516288569 I think that's 20. So, half a mole of helium gas is put in a 5-liter steel container. The pressure of the gas is at 31.516288569 degrees Celsius, and the pressure is 2.5 atmospheres. If 0.1 moles of the gas is allowed to escape and the temperature drops to 20 degrees Celsius, what is the pressure of the gas? So let's look at only the final values. So we know the ideal gas law states that pressure times volume is equal to the number of moles times some R constant, gas constant, times temperature. And I'll let these all be final values. So we're solving for P2. So the final number of moles would be 0.4 because it lost. So it started out with a half a mole and lost 0.1 moles. Its final temperature would be 20 degrees Celsius, which is the same thing as 293.15 Kelvin. The final volume, we assume that steel container isn't going to move, so the volume stays 5 liters. And that's all the information we need to know to solve this. We're solving for final pressure. So final pressure would be equal to the final number of moles times R constant times final temperature over initial volume. You really didn't even have to include these 2's. I worded this problem because notice we didn't need to know the initial pressure. We didn't need to know, really know, we need to know how many moles we start with, only because we need to subtract 0.1 from it. We didn't need to know the temperature, the initial temperature. All we needed to know was final temperature, or I should say current temperature, current number of moles, current volume, and we can calculate pressure. So plugging this in, 0.4 mole. Remember that the abbreviation for moles is MOL, not MOLS. The R constant is 0.082057 and it's in liters, atmospheres, Kelvin, mole, times a temperature of 293.15 Kelvin. I might have used a slightly different value of R constant. But we would select the one that uses atmospheres. Then we divide by volume. Volume is 5 liters. Check to make sure that everything cancels out. So liter divided by liter. Moles on the denominator times mole on the numerator. Kelvin and Kelvin. And we're left with atmospheres. The pressure inside would be 1.92441 atmospheres. Everyone good? That's atmosphere. It was a Kelvin times a mole. So K times mole. By the way, if you ever see this notation, so the R constant, R was equal to L times atmosphere times Kelvin to the negative 1 times mole to the negative 1. What does it mean when I say X raised to the negative 1 power? Y'all know what X to the negative 1 is? What about X to the negative 2? What about X to the negative 1 half? Or what about X to the 1 half? What is X to the 1 half? That's the square root of X. This is just 1 over X. This is 1 over X squared. This is 1 over the square root of X. So if you have something raised to a negative exponent, it just means it's the inverse. So X to the negative 1 is 1X. X to the negative 2, you can flip it to the exponents. Have y'all not done exponents in math classes? Yeah, I should have been taught exponents. So what K to the negative 1 just means, that's the same thing as the units of L atmosphere divided by K divided by mole. So if you see something raised to the -1 power, it just means that it's really being divided by that. I'll go ahead and do the code word. So for remote learners, there's the code word. Yes. You have a water bottle. How many milliliters is it? How much? Yeah, that's what I said. Suppose you have an empty 500 milliliter bottle in your vehicle. What's a good temperature right now? 77? So, and you closed it at 77 degrees Fahrenheit, which is equal to 298.15 Kelvin. And what temperature does it fall down at night? Let's do that. What's the high for today and low for today? And what's the high? 72? We'll use 77. Make it farther apart. So, during the night, it cools to 66 degrees Fahrenheit, which is the same thing as 292.039 Kelvin. What is the volume? Of the water bottle? 0.039 at night. So initial volume is 500 milliliters. Initial temperature was 298.15 Kelvin. We're solving for final volume. And the final temperature was 292.039 Kelvin. See if you'd even notice a change. So T1, so let's do PV over T equal PV over T. Here's our initials. Not concerned with pressure in this problem. These should be 2's. So we have V1 over T1 equal V2 over T2. So we're solving for final volume. So final volume is being divided by T2. So to move T2 to the other side, we do the opposite of division, which is multiplication. So you move this to the other side by doing multiplication. So V2 thus equal to temperature 2, which is 292.039 Kelvin, times initial volume, 500 milliliters, divided by initial temperature. Kelvin is going to cancel out. And you'd see it lose a little over 10 milliliters of air. Won't lose it, it'll shrink by that much volume. Probably wouldn't notice it. So 11 degree drop in Fahrenheit doesn't really change too much. Dang, it's an empty bottle. It's air. So the air is compressing.